Welcome to the demonstration for my software project, Sun Elevation Calculator. Sun Elevation Calculator is an iOS application that can be used to calculate the elevation of the sun above the horizon for a given day and place. The user selects a location, a date, and interval, and the application returns a table of sun angles for that day, highlighting angles greater or equal to 50 degrees in yellow. Throughout the day, as the Earth rotates, the sun's angle in relation to the horizon changes. In the northern hemisphere, the sun's path is longer in the summer months and reaches greater angles of elevation, which translates into longer days and greater intensity of ultraviolet rays. While UVA rays are always present during daylight hours, and UVC rays are blocked by the ozone layer, the presence of UVB light varies as a function of the sun's angle. The shortest length of intersection between light rays and the ozone layer occurs with a sun elevation of 90 degrees. At angles less than 50 degrees, UVB rays are overwhelmed by the long path of intersection. One reason UVB is of relevance to us is because it's the only type of sun exposure that causes the production of vitamin D in the body. Now for a brief demo of version 1 features. Selecting Calculate by Coordinates pre-populates latitude and longitude values using the user's location. The date is pre-populated to the current date, and the default interval is 5 minutes. We see in this case no highlighted section in midday, meaning the sun in San Francisco on January 22nd never gets 50 degrees or greater above the horizon. Now changing the date 2 months forward, we can see that UVB rays are present between 12 and 1 on that day and gone by 2 p.m. I can also compute by city, which is pre-populated per the user's location. Again, looking forward by 2 months, this time looking at intervals of 5 minutes, I can see more detail on the sun's angle, which is actually greater than 50 degrees until 1:35 that day. The Earth System Research Laboratory provides a browser calculator to obtain the same information. Input is in degrees, minutes, seconds rather than decimal coordinates, so here I enter coordinates for San Francisco based on degrees, minutes, and seconds in their system. The selected time is 12:05 p.m., for which my calculator reports an elevation of 32.454. Their calculator reports an elevation of 32.47, so the variation is small, in this case to 0.02 of a decimal. The table calculation is done on a backend, which I've implemented in Google Cloud in Python. For the backend of version 1, I created 2 API routes, one for inputs of city names, states, and countries, the other for input of coordinates. The angle calculation is done with this MIT license code, however with a few significant modifications. For instance, the original code returns all values in UTC, meaning results are off by a factor of the requested location's time zone. For San Francisco, that meant the original code had the peak elevation 8 hours later than it actually is. To solve this issue, I used Google's geocoding API to find the time zone offset in seconds, so as to convert the results into the correct time. The original code is also limited in that it can only handle input in coordinates, not in city names, states, and countries. I made another geocoding API call to Google in order to convert incoming addresses to coordinates. The front end is done in Swift and Xcode with UIKit. Core Location and MapKit are used for pre-population of user location. Results are given in a UI table for its ability to handle uniform data points and variability in result length. Lastly, I've implemented error handling on the front and back end. For instance, when the user enters a city-country combination that cannot be found in geocoding, or enters invalid coordinates, my API backend returns a 400 error code, which the front end converts to an informative message for the user. For version 2, I will implement notification features as well as full-year data inquiries. The user will be able to request push notifications when the sun is about to ascend above 50 degrees. They will also be able to take a year-long look at the sun path for a region in order to see the time span in which UVB will be present in the atmosphere. These features will require that I add additional API routes as well as front-end pages. You can find the front-end code for this project on GitHub, which I've linked in the description below. Once version 2 features are implemented, I will be submitting the application to the iOS App Store. Thanks for watching.